Hello, welcome everyone. Okay, take another second to think about these four substances, what's happening with them in the proximal tubule, which is where we left off on Friday. If you don't get to all of these by the time I start talking, don't worry about that. You can come back and use these as practice problems when you get to studying for the exam. Okay. Looks like we may have everybody with us for today. So let's remember where we left off with the proximal tubule, because today we're going to finish up with that and start to talk about water balance. So you'd already talked a lot about sodium chloride and water, what's happening with them in the proximal tubule, namely that there's a sodium-potassium pump on the basolateral membrane. I will actually pull up our slide where we are looking at this. So what we were looking at was this diagram they have in chapter 18, which doesn't actually tell you which molecule is which, but I can tell you perfectly fine. So when we're talking about sodium, we're really talking about solute Y here. So what's going on with sodium is that we have a sodium-potassium pump here on the basolateral membrane, which is the part that faces the peritubular fluid, which is the small space between the epithelium and our capillary endothelial cells. So what we do is we pump sodium here into this peritubular fluid, which is creating low sodium inside the cell, which means that sodium moves passively down its gradient towards that area of low sodium, and then would be pumped into the peritubular fluid, creating high sodium here in the peritubular fluid, which can then move passively into the capillary down its gradient again. So that's what's going on with sodium. Chloride and also water are basically following this gradient. So if we jump down to Z, that's kind of what's happening with chloride following along with sodium. And water then is moving along this gradient as well, because we know that as we build up solutes, right, as we have lots and lots of sodium here, right, we're making it salty. Sodium can't cross the membrane without a channel, so water moves to water it down, right, by osmosis. Okay. When we get to glucose, was where we started talking about transport maximum and transport threshold. So I think this is the slide we left off with on Friday, introducing this idea of the transport maximum. So the transport maximum just refers to the fact that there's a certain rate of transport at which all carriers, so all of the proteins for that specific molecule are saturated or full. And therefore, even if we have more of that molecule in our filtrate moving through the nephron, we won't be able to move more across that epithelium because we don't have enough carriers. Okay, so the renal threshold, this term, the renal threshold, refers to that maximum rate where we have a solute that can be 100% reabsorbed. So this is really kind of our point where everything is full, but we don't have any spillover, is the renal threshold. If we go over the renal threshold and we fully saturate the carriers and keep bringing more of that molecule, then we are going to have some of the solute excreted in the urine. And in practice, the renal threshold, like the actual renal threshold, will be a little lower than the theoretical renal threshold, because as we reach saturation, right, the way that molecules get carried across the epithelium does first depend on them coming into contact with a carrier in the cell membrane, right? Like they have to bump into it. And as more and more of them are full, some of them are gonna just like pass by too quickly before they bump into an empty one. So we'll see the numbers for that for glucose in a second. Okay, so when we have solute in the plasma going really fast through the filtrate, we're above the renal threshold, we'll saturate the carriers and spill over into the urine. Okay. So our example for this, and the large reason we care about this, is with glucose reabsorption. So it's freely filtered at the glomerulus, meaning that all the glucose that's in the plasma, right, moves into the nephron at equivalent concentration, right? It's filtered into our nephron. Now, usually we want it to be 100% reabsorbed in the proximal tubule. So we want to take back all our glucose to use it for energy, which means we wouldn't see any glucose in the urine. But if we hit the renal threshold for glucose, then we're going to start to have spillover. So we would start to see glucose in the urine. Our carrier proteins for the glucose specifically, we'll see a diagram in chapter 19 showing us where they are. But for right now, you can have this preview on the apical membrane. So that's the part facing the filtrate, so facing the inside of the nephron. We have secondary active transport going on. So we have a carrier protein that uses the sodium gradient, actually, to actively transport glucose into those epithelial cells. This has the effect of basically concentrating glucose in the epithelial cells, so then they can cross the basolateral membrane on the side facing the blood via facilitated diffusion, right? Which means that we do have a protein that glucose has to go through because glucose can't squeeze through phospholipids, right? It does need a protein to allow it through, but this would be a form of passive transport across that basolateral membrane because glucose will move down its concentration gradient. So we'll often think about the transport maximum when we're trying to figure out how the kidneys are handling glucose. So renal handling of glucose is an important topic. So usually in our plasma, we have a concentration of 100 milligrams per deciliter, which we know to find the filtered load, we multiply by the GFR, which is 125, giving us 125 milligrams per minute. So at this concentration and this GFR, we're totally fine. We can reabsorb 100% of that glucose. Now, our theoretical transport maximum, so if we were using every single, I'll pick a blue because they're red, okay, every single transporter here. All right, so here, just highlighting, we see our secondary active transport happening at the apical membrane. And here we see where our facilitated diffusion is happening on the basolateral membrane. But if we were to fill up every one of these carriers, right, we could have another one here, right, glucose coming in, but they're all full, that would be our transport maximum. And the theoretical transport maximum, where every one of those carriers is used, is 375 milligrams per minute. So if your blood glucose was at 375 milligrams per minute, that's when theoretically you would start to see spillover into the urine. Or we have some slightly different numbers because this also depends on the GFR. So to get the transport maximum, the way we did it was we multiplied the GFR by the renal threshold to get our transport maximum, I should say. So this turns it into a rate, basically. So the theoretical renal threshold, we'll note, is in milligrams per deciliter, and our transport maximum is milligrams per minute. So we multiplied it by the GFR so that we could figure out what it was per minute. That's how we got there. Right. Okay. Now the actual renal threshold is lower than this. And that's because of this fact that as we start to fill up, as we start to saturate those carriers, it becomes more and more difficult for glucose to find a carrier that's open as it's rushing past. So the actual renal threshold for glucose is only in this range of 160 to 180 milligrams per deciliter. So as soon as your blood concentration of glucose starts to get into or above this range, and this depends a little person to person, this is when you're going to start to have spillover into the urine. So this is usually around the range where we would mark pre-diabetes or diabetes, depending on when we measured the plasma glucose, because when we're actually defining diabetes, it depends how recently you've eaten when we look at the blood glucose. Okay, so this actual renal threshold corresponds to a filtered load of 225 milligrams per minute. And we actually did out this calculation at the beginning of Friday. That was our warm-up problem. So if you don't remember that, don't remember how to calculate that filtered load, you can go back and take a look. That video is up. Okay. We could also graph some of our relationships here when we're thinking about glucose. So what we see here on the y-axis is our rate of glucose movement, right? So basically our filtered load of glucose, how much glucose is getting into the nephron, and our plasma concentration of glucose. So what we see happening, right, for filtration, sorry, I misspoke. So for filtration, this is the line expressing how much glucose is getting into the nephron. And this is only dependent on that plasma concentration of glucose. So even though they kind of skewed the axes, which is annoying, you can see that this is almost approximately equal, right? It's a straight line. If there's more glucose here in the plasma, there's going to be more filtration of glucose, more movement of glucose into the nephron. Okay. If we look at the reabsorption of glucose, this relationship will be the same, right? More glucose in the plasma means we'll reabsorb more glucose, but it's only true to a point. As we start to reach this renal threshold, it becomes more and more difficult to move glucose across the epithelium, right? Because those carriers are filling up. So when we reach the total transport maximum, we will see that we flatten off into a plateau because we're completely saturated. We can't absorb anymore because we don't have any carriers for it. You see this kind of tapering off region right here where we're slowly reaching that plateau because of that fact that in this region we would have some open carriers, but they're hard to find. Okay. Now finally, we see the excretion rate on the bottom. So excretion is how much glucose would be in your urine. So long as we're in the amount of glucose that we can tolerate, that we can move effectively, we see no glucose in the urine. And this is basically the opposite of the reabsorption line, right? So we start to see it move up, increasing in speed as our nephron, as those proximal tubules are having difficulty reabsorbing the glucose into the blood. And eventually, right, we'll reach a straight line where any more glucose, right, is just going to be immediately excreted because we've reached our saturation point. Okay. This brings us to the topic of secretion, right? Not excretion, secretion. So in secretion, we're going to have the movement of molecules from the blood into the filtrate. All right, so we talked about this a little when we defined each of these terms when we saw this diagram the first time. So the barriers are going to be the same as for reabsorption. So we're going to have to cross the epithelial layer of the nephron, of these tubules in this case. We're going to have to cross this peritubular space. All right, we just got a little fluid there. Then we're going to have to cross the endothelial layer of the capillary in order to get into the bloodstream, into the plasma. The transport mechanisms for this are the same. Namely, we do use carrier proteins, but they just work in the opposite direction. So they'd just be pumping stuff into the tubule rather than with reabsorption. Occasionally we see stuff pumped out. So some of the secreted substances that you'll see are listed below: potassium, hydrogen ions, choline, creatinine, and penicillin. So all of these things at different points in the nephron would get added into that filtrate, right? So these are all things that you might expect to see in the urine and be excreted eventually. And when these become important, a couple of them will become important. We'll see like hydrogen ions. We'll talk about them where these secretions are occurring. So we do have renal specialization of the renal tubules, which is to say that we have different things happening in the proximal tubule, right? This is our proximal convoluted tubule, this part. We have different stuff happening there than we have happening in the distal convoluted tubule, which is here. All right, so this is our distal convoluted tubule, and they have the loop of Henle between them. Okay. So the proximal tubule are a big bulk reabsorber. So we're going to have pretty much unregulated reabsorption. We're just going to have lots and lots of stuff coming out of the proximal tubule and back into our bloodstream by getting into the peritubular capillaries. But when we get to the distal convoluted tubule, we're going to see that everything is much more regulated. We're going to see the influence of hormones here. So we're going to have regulated reabsorption, and the distal tubules are really where we'll see secretion. We don't see much secretion in the proximal tubule. So the secretion is going to be happening basically at the end of the nephron, so in these distal convoluted tubules and in the collecting duct. And we will talk about those as we get to the specific secretions and the specific secretions and the specific things we're interested in crossing these membranes and the hormones involved. So that is in chapter 19. Okay. Finally, most of our water is being absorbed in the peritubular capillaries, but we'll also see that water conservation is happening in this loop of Henle down here, which we'll talk about in super deep detail. Less of the water is being reabsorbed there in the loop of Henle, but it's really important to water conservation. So that's a big point when we get into our next set of slides on water balance. Okay. So this is just a restatement of some of these things we've talked about already so far. So that proximal tubule right? The proximal tubule is here, this first part that we have after our renal corpuscle, the glomerulus, and Bowman's capsule, right? It's reabsorbing 70% of the sodium and water that gets into the filtrate. It's reabsorbing 100% of the glucose, right? So long as we are below our renal threshold. Okay. And the reason it can do that is partially to do with its histology. So as we've been looking at these cells, we've really been looking at proximal tubule cells. So we can see at the apical membrane, we have this large surface area created by these microvilli. And we refer to this overall kind of bristly layer as our brush border, right? So it looks like a brush. This is our brush border. It's on the apical side, which is the side facing the filtrate, so the stuff that will eventually become urine. There are tight junctions between the epithelium. So big things can't get between these cells, but they are a little leaky, so they do let like chloride through. So we do have some paracellular transport going on here, right? Because we want to reabsorb tons and tons of stuff. We're a mass reabsorber here. So this is a little different than what we see in the distal tubule. This is just a zoomed in picture of that picture from the previous slide. So in the distal tubule and in the collecting ducts, we'll see a couple differences. All right, so one thing, right, we don't have a brush border here, right? We don't see all those microvilli forming that sort of bristly look. So we have less surface area here for reabsorption. What we're doing instead is we're really tightly regulating what will get reabsorbed here and also secreted. So our tight junctions are much tighter as well, which means we're really limiting paracellular transport. So we're really limiting what can kind of just sneak right by these cells. Okay, so we can compare these two cells. Just going to flip back so that you can appreciate, right, difference between a proximal tubule cell and a distal tubule cell. We will see that both have like lots of mitochondria, right? Because they are going to be needing ATP, right, to fuel their sodium pumps, for example. So there are some similarities, but there are some really important differences. Okay, this is just a zoomed in picture again of that distal tubule. Okay. So after we go through the paratubular capillaries with their bulk or mass reabsorption of water, sodium, chloride, and literally all your glucose, we're going to enter the loop of Henle, which is starting about here. So the loop of Henle is this kind of U-bend, kind of looks like a trombone, right? This is what's going to be establishing gradients that are necessary for concentrating the urine. So we're going to see more water reabsorption here. We saw that 70% of that water was reabsorbed in the proximal tubule, but when we looked way back, I'm not sure it was on Friday, it might have been on Wednesday, when we looked at the amount of the water that gets reabsorbed, we saw it was in the high 90s, right, percentage-wise. So the rest of that is going to be happening in the loop of Henle. And we'll talk about how it establishes this gradient and how that allows us to concentrate urine as we move into chapter 19. Okay. Before we do that, we want to touch briefly on excretion. So we're going to talk briefly about the excretion rate, so how fast things are excreted, the concept of clearance, and we'll have a brief reminder on what micturition means. Okay. So when we're talking about the excretion rate, all we're basically saying is that the amount of substance excreted, which is the amount of that substance that's in your urine, right? So the amount of water in your urine, the amount of glucose in your urine, the amount of sodium in your urine, whatever substance we're tracking. So the amount of substance excreted is going to be the amount filtered, right? So our amount filtered, which is the amount that would get into the nephron, right? As we are pushing our plasma through those glomerular capillaries, right? So this is basically kind of going to be your filtered load approximately, plus the amount secreted. So any additional molecules that we put into there, so any additional amount that moves back into the filtrate from the paratubular capillaries, for example, minus the amount that we reabsorbed, right? Minus the amount that we moved from the filtrate into the blood. So I think that this is easiest to follow if we look through this table of what's happening. But basically we're tracking three factors. We're tracking the filtered load, right, which is what's getting into the nephron, the secretion rate, which is all the sort of fiddly regulated putting of ions and things back into the urine that happens, and the reabsorption rate. So we're subtracting out whatever we move from that filtrate, from the liquid that's going to eventually be urine, into the blood. So we can compare if the amount of solute excreted, so the amount that ends up in your urine, is less than the filtered load, right? Less than the filtered load, which was the amount that got into the nephron. We know solute had to be reabsorbed, right? Because like if you put 100 of something in, right? We'll go through the real example actually. So stay tuned. If the amount of solute excreted per minute, again, the amount that gets in your urine, is greater than the filtered load, this means solute was secreted, so it means we put in additional stuff. Okay. So I think our next slide is a zoomed in picture of this stuff on the right. Yeah, so here we can track kind of what's happening exactly with some numbers, right? So here we see our solute, right? So let's say our solute is being filtered, so our filtered load is 12 millimoles, right? So that is how much we are filtering into our nephron, right? I'm going to jump to the end of this equation so we can then kind of understand those comparisons that we had at the bottom of the previous slide. So if our solute has 12 millimoles filtered in and only 9 comes out, right? This means that overall, something had to happen to those additional 3 millimoles, right? Like, why are they not in the urine? The answer to that, the answer of why they are not in the urine, is that on net, we have reabsorption, right? So the reason they're not in the urine is because we move them back into the blood. So we do compare the amount secreted and the amount reabsorbed. So this is why we only have a difference of 3 rather than a difference of 6, because we basically took that 12, we added through secretion 3 millimoles, right? So this brings us up to 15, right? And then we're saying that we reabsorbed, so moved back into the blood 9 millimoles. So that's how we get down to 9. Okay, so that's how we're conceptually moving stuff across. This is not, I will note, in the order it would happen in the nephron. This is in the order of the equation. Usually we're going to see reabsorption happening first and then secretion happening later on in the nephron. Okay, so we can also do this with water. So just like we can do it with a solute, we could say, okay, if we got 150 milliliters of water into our filtrate, we're not actually going to secrete water, but we are going to reabsorb a ton of water, right? 145 milliliters, leaving us with only 5 milliliters in the urine, which is good because we want to keep most of our water for blood volume. Okay. So if we wanted to see something that was secreted overall, we would shift these numbers between secretion and reabsorption, right? Which would then give us a higher number here, right? If we were secreting a bunch more than we were reabsorbing, right? Say we were secreting 7, let's say we're reabsorbing 6 still. We do 12 plus 7 minus 6, so we'd get like 13 millimoles. Okay, so that's all that comparison was doing, was telling you you can compare this versus this, and you'll actually know something about the relative balance of secretion versus reabsorption here. But if you think of it in order, and I often do kind of little tester equations with fake numbers when I get confused about comparisons like that. This is pretty obvious as you practice through, even though memorizing that comparison may be a little confusing. Okay. So here we have a table of the clearance of some common substances from the kidney. So when we refer to the clearance, what we're saying is the number of milliliters per minute that is going to end up in the urine, essentially. Okay, so here we can see our clearance rate for PAH, creatinine, insulin, potassium, chloride, sodium, right? So here we have positive clearance rates for all of these, so we are going to see some of them in the urine. And some of this on net for renal processing is going to be secretion, and some is going to be reabsorption. So this note at the bottom here is important. So when we have clearance that is greater than the glomerular filtration rate, that means that net secretion has occurred. So right, like if we have more in the urine than we were moving into the nephron originally, that means we had to secrete it into that filtrate. If we have less than we moved in, then net reabsorption is happening because it means we're not ending up with all of it in our urine. So that's why we have some things that are secreted, some things that are reabsorbed. So we talked a little bit about micturition when we talked about the anatomy of the bladder. So we're actually going to skip most of these slides, but I'm just going to kind of remind you what this word means, because I think that's really the important thing for you guys to know moving forward. So micturition is just a kind of technical term for urination. So what we're doing with our nephrons overall, right, is we're taking plasma, filtering it into the nephron as filtrate. We're adjusting it by reabsorbing and secreting things, forming urine. That urine then moves into the renal tubules, drains out of the kidneys, so out of the renal pelvis into the ureters. Right, so we would have a kidney up here, drain into the ureter, which leads to the bladder. The bladder stores the urine until it's excreted. So the things we care about here, right, is the bladder is largely made up of this muscle called the detrusor muscle. We have an internal urethral sphincter and we have an external urethral sphincter. The external one is the one that's under conscious control, while the internal urethral sphincter is largely responding to involuntary factors, things like pressure. So if you are curious, there is a sort of long list of steps here on how exactly this is controlled. But we're not talking a lot about the neurons involved in this chapter, so I'm going to tell you to skip this, at least for the purposes of the exam. Although if you read through this and you have questions, we can absolutely talk about this later. So it is controlled. Based largely on stretch. There are nerves that do this because we have muscles, right? So we need to have nerves. Okay, and this is a flow chart of what that process would look like. So I'll give you a second to pull up your PowerPoint on balance. So part 1, and we're gonna move into that now. So we're largely gonna be talking about how water is conserved. Okay. So here are our objectives. We want to understand the concept of balance. We want to understand body water input and output. And we want to understand how water balance and osmolarity, so like solute concentrations and pull on water, are controlled by antidiuretic hormone, ADH, or vasopressin. So we're going to start with this idea of balance. So when we're talking about water balance, which is mainly why we care about balance, really all we're talking about is a version of maintaining homeostasis, right? To have consistent internal conditions, we need to have consistent concentrations of things in water, of molecules in water in the plasma, because that plasma is circulating around the cardiovascular system. It's reaching equilibrium with the interstitial fluid. So we need to maintain its concentrations and its water content similar, or we're going to mess up what the cells are doing, because we're going to mess up what all their gradients are. And we know that all sorts of processes are really dependent upon the gradients across membranes. So when we say something is in balance, what we really just mean is that in equals out. So the amount of our thing, specifically water, the amount of water input into our system, so the amount you're drinking, plus anything your cells are producing. So here's where we want to remember that water actually is a byproduct of cellular metabolism, should equal the amount of water you used, right? We know like hydrolysis reactions exist, right? Like we use water to break things up sometimes, plus the water your output, right? So this is our inside, this is our outside. So if this works, if in does equal out, then we are in balance. So a large part of this is going to involve the kidneys. So the kidneys are going to be regulating the solute and water content, so like sodium, like our ions, as well as the water, which is going to determine blood volume, which is going to be basically the thing we're regulating to keep in balance. Your kidneys also regulate acid-base balance, which we're not talking about yet, but we will. Another note here is just so that you are aware, there is exchange between different compartments of the body. And so the composition of your plasma, right, is going to depend what's going on in your cells, what's going on in your connective tissue, what's going on in your GI tract. Are you sweating? How fast are you breathing? What's the content of that? So it is dependent on exchange at all these places. So we want to think a little bit about where body water comes from and how it leaves the body. So this is a big, kind of messy looking diagram, but it's actually pretty simple if we think about it in order. So the first flow we want to think about is drinking, well, and eating, right? So what we have happen, right, when we drink or when we eat, right, we ingest food with water in it, or we drink water directly, gets into our digestive tract, and then it either gets excreted through the kidneys or ends up in our feces potentially, right? So that's just moving us through the pipe from our mouth out our anus, right? From here, we also see absorption, right, into the plasma. So this on the right-hand side is going to be directly really tracking what's happening in our kidneys as we move here. So a thing we can have happen, right, is that water gets absorbed from the GI tract into our bloodstream, and then it gets filtered into our nephrons, so into the renal tubules. It's excreted out as urine. Okay, so that's where they put the urine on here. This is showing us that secretion may also play a role. Reabsorption back from the renal tubules also adds to plasma and interstitial fluid water. We're going to have water coming in or potentially coming out from our cells' connective tissue. We may be losing water to things like sweating, hemorrhage, and respiration. So you don't really have to memorize this table. We're going to go through whatever parts we think are important. So we may be secreting things back. But this is what a big, like, sort of web of all these processes would look like. Okay. So when we're thinking solute and water balance, right, we're thinking does in equal out. So we want to think about the solutes and water entering versus exiting the plasma. If they enter and leave at the same rate, right? So if the amount we put in is the same as the amount we take out, the quantity is going to stay the same, right? So this would maintain your blood volume, and it would maintain the appropriate osmolarity of your blood, of your plasma, right? So if we keep everything the same, anything we put in, we take out, we're good, we're in balance. We do also use these terms positive balance and negative balance. So these are deviations from the in equals out situation, right? In positive balance, what we're saying is that you're putting in more than you're taking out, right? So if you put in more, the amount of that water, of that solute, is going to increase, right? Because you're not like deleting everything you put in. So that's positive balance. So positive is about the direction rather than like, yay, we like it, right? It's positive because this is an increase. Versus negative balance means we're taking out more than we're putting in. So negative, again, is about direction, not about whether we like it or not. So negative, we're going to have a decrease because we're taking a lot out. So we want to be in balance. Right? But we will sometimes have to use these positive and negative balances in order to correct previous deviations, I guess I should say. Some of the cells that are going to be involved are a little important, have some special names. So when we talk about cells in the late distal tubule and in the collecting duct, this is really where we're regulating balance. So we said that the distal tubule, right, the distal convoluted tubule is where we're really going to have regulated reabsorption and secretion, right? So what we're really regulating here is making sure that we're in balance. And we are balancing water and electrolytes. We are also balancing blood pH, so plasma pH. So acid balance has its own special cells that control that acid-base balance. So the principal cells, right, are here. So this is looking at a collecting duct cell, but it would look similar in the late distal tubules. So as they're entering the collecting duct, basically, kind of at the junction. So principal cell would look like this. This is helping us move water and electrolytes to maintain balance of solutes and of water. And the intercalated cells look like this, right? So we can see now that they actually do have microvilli, right? And we'll talk about these later when we talk about acid-base balance, but they're helping us maintain appropriate pH in the plasma. So we have these two types of cells that we think about when we think about balance, depending on what type of balance we're thinking about, like what molecule we're balancing. Okay. So Now we want to dive in deep to the idea of water balance, which is kind of inextricably tied to osmolarity, because we remember that osmolarity is about the concentration of solutes dissolved in water or dissolved in plasma, and it exerts a pull on water. So we need to remember that we have solutes exerting a pull on water in order to understand which way water is going to move. So these two things are tied together. And our big hormone that we think about when we think about water balance is something called Antidiuretic Hormone, ADH, sometimes also called vasopressin. Okay. So we're going to be thinking about osmolarity and how it moves water. We're going to think about water reabsorption, which we've already looked at how that happens, right? We already looked at the fact that 70% of our water is being reabsorbed in the proximal tubule. Now we're going to go into more detail on the remaining water reabsorption that is happening in the loop of Henle. So we're going to talk about how the medullary osmotic gradient gets established and how that affects the movement of water in the loop of Henle, but also in the distal tubule and the collecting duct. So we'll move forward into that. Okay. Before we directly do that, just one more time about water balance, right? So water balance means essentially in equals out. All right, so we have water intake equivalent to our water being output, right? So when we're excreting it in urine or feces. But we want to make sure we add our slightly smaller quantities of water that we produced through metabolism and water that we used up in various metabolic processes, various chemical reactions happening in our cells. Right. So this is just that diagram again, but they've highlighted where we're inputting water and where we're taking water out. Okay. So water is coming in through your GI tract when you eat or drink something that contains water. Also counts as in if we're thinking about the water produced in cellular metabolism. As we break down glucose, we produce water. Output is just all sorts of ways that water leaves our system. So it may leave through the GI tract, it may leave through the kidneys and become urine, it may leave through sweating, may leave through insensible loss, which might be things like breathing. Okay. Zoomed in. Basically, this is just showing up here to show us that these actually do add up together. Usually people ingest about 2.2 liters of water per day between their food and drink. Cellular metabolism usually produces about 0.3 liters, giving us 2.5 liters per day. And that is equivalent to our water outputs. Okay, so usually you excrete in feces 1 liter of water per day. You excrete as urine 1.5 liters of water per day. Other various losses are about 0.9 liters today. So that adds up to our same number as before, meaning we're in water balance, meaning that our blood volume stays the same, which is great for us. We can refer to the effects of water balance on blood volume using specialized terms. So before we saw balance versus positive balance versus negative balance, that had to do with directly talking about that equation, like are we increasing water, are we decreasing water? But what we normally care about in a clinical setting is really blood volume, unless we're looking at the kidney specifically. If you're a kidney doctor, you can erase that sentence, a nephrologist. So normovolemia means we have normal blood volume. Hypervolemia, hyper means more, right? So we have high blood volume due to positive water balance, right? Because we have more input than we have output. Hypovolemia, hypo always means low. So if we had low blood volume, volemia, that would be due to negative water balance. So basically you'd be losing more water than you are taking in. Okay, so we will stop there for today and we'll pick up next time talking about osmosis, osmolarity, and the loop of Henle.